Thales Student Innovation Championship 2018 Artificial Intelligence Case Study Summary. For a given topic provided by the end user, propose innovative algorithm which will collect all available opinions and their supporting evidences. For an example, articles, images, videos, text, etc. Validate every piece of evidence, weighting its contribution to the topic and explaining this contribution. Show which pieces of evidence are in align or contradiction with the topic. Group evidences to different opinion clusters. Allow the system to explain and visualize its decision-making process. So we are the team Rococo Basilisk presenting our product called SPDYBOT, which is Speedy Spider Robot. We won the third prize for the Canadian $5,000, and we are the contributors from the University of Windsor, alphabetically listed as Kaival Patel, Ruturaj Rawal, Zarin Nawal Reza. This is us. This is the outline which we are going to discuss today. From introduction to problem statement, from model architecture to algorithm explanation, including feasibility and cost analysis, challenges, product prototype, comparison to alternatives, and the conclusion. Introduction. A survey suggests that as of June 2018, 4.2 billion people use internet. Abundant access to the internet has enabled people to have access to unlimited benefits including freedom to express opinions, be it positive or negative. It can influence decision-making policies actively and passively. Background. Freedom of speech brings divergent opinions based on political, financial, social, commercial, or religion, etc. aspects. People's opinions can offer favor or criticism to any topic. Valid opinions are crucial to take important business, political, or social decisions. For an example, business enterprise can change the behavior of their entities based on customers' opinions and the preferences. However, finding the valid opinions and the claims and disregarding the misleading ones is very challenging. Therefore, every opinion and claims have to be backed by relevant evidences. The process could be biased if the number of participants grows. Problem statement and solution overview. Manually surfing and analyzing each and every opinion is a mere impossible task. We are providing an AI-based solution which can automatically collect all the opinions and claims related to any topic and gather sufficient evidences to validate them. We have divided the whole task into 4 subtasks, which are sequentially dependent to each other. The core of our solution uses a concatenation of 2 deep convolutional neural networks for each of the subtasks. It is an end-to-end learning model without human participation. It is very simple to design.
I would like to give an overview of our entire model through this architecture. Instead of building a very complex model, we have focused on building a subtask-based multiple specialized models which are simple to design, very efficient, and easy to interpret. We have divided our entire task into 4 subtasks, namely as information retrieval, claim detection, evidence collection, and evidence classification. Also, it is an end-to-end learning model. The only input to this model is a query or topic provided by the user, which is passed to a web search engine associated with a CNN-based IR model. The core part of the solution is a multiple CNN concatenated model, which I am going to explain in later slides. So our IR model will help the search engine to retrieve web pages that are most semantically relevant to the user topic. From each of the retrieved web pages, we will do both multimedia mining and text mining. For images, we will be using deep neural net for image captioning, whereas for videos, video transcript is generated through speech-to-text conversion. Also, as an advanced technique, we can do video captioning when there is not enough speech. For text mining, each sentence components are parsed from web pages. Both the multimedia transcript and text data are passed to the next module, which is trained to detect if a certain sentence is a claim or not. All the sentences detected as claims will be then passed to the next CNN model for evidence classification. Again, this model is trained to collect context-dependent evidences where each of the claims are context. This model will return a dictionary containing each claims with their corresponding evidences. The claims with no evidences will be discarded. The output to this model is passed to the final CNN model for evidence classification. This model is trained on textual entailment dataset, which will classify each evidence as entailing, contradicting, or neutral in terms of the claims. Finally, we have this visualization technique associated to a word embedding pre-trained on a word2vec, which will provide the final output in numeric form to the user and also will provide explanation to the whole decision-making process. Let's go through a small example of CNN in NLP. Here we have a sentence with 7 words. Let's assume our word embedding is a 5-dimensional word vector. So we have this 7 by 5 matrix. Let's see, we have 3 filter regions of size 2, 3, and 4 having 2 filters each. Finally, there is a max over time pooling layer followed by activation function, which gives 6 activation vectors concatenated together to form a single feature vector. That's how, even if we have variable length input, we can always have a fixed length of output which is needed for the classification purpose. Also, we keep the special information of word sequences in the sentence, which is important for NLP tasks. The core of our solution is a concatenation of 2 CNN models. One is for encoding the context and the other one is for encoding the target. As we see, after convolution layers and pooling layers, both sequences are represented as feature vectors. Using these vectors, we can calculate the cosine similarity of the sentences, which will tell us how relevant the target sentence is to the context sentence. Also, there are different hyperparameters we have to set, which can be optimized during training and evaluating on validation set. Word embeddings are word2vec, which are pre-trained on Google News dataset with 3 million words with 300 dimensional word vectors. For the second and third modules, pre-trained words embeddings are fine-tuned with respective dataset corpus. First module is trained for information retrieval, or in other words, opinion collection. Model is trained on click-through data logged by a commercial search engine. Here, context is the query topic and target sentence is the web page titles. Based on the cosine similarity score, we will know how much a web page is semantically related to the query. As example, from this paper, as we can see that for the query Microsoft Office software, free Office 2000 has higher similarity score than International Office Berkeley. Next module works for detecting which of the sentences from the retrieved web pages are opinion and claim. The model is trained on subset of database dataset provided by IBM for claim and opinion detection. Finally, as we can see, a softmax classifier layer will predict the probability for each detected sentence being an opinion or claim, and the model keeps all the claims having probability score above a threshold. For multimedia mining, image and videos are mined using deep learning technique as well. As example, images are mined using VGG16 deep convolutional neural net pre-trained on ImageNet. We have multimedia content extractor, which extracts all the images that are present in a given web page and filter the ones that do not contain useful information like advertisements, banners, etc. It also discards the images that contain a specific group of keywords in the attribute or in the image caption. It also rejects images whose dimensions are outside of a specific range, like a logo. It generates image captions using deep learning. For video, document is generated using speech-to-text converter, and for advanced technique, video captioning using deep learning can be used. In next stage, each detected claims and opinions from vector will be passed through next CNN concatenated model, which is trained on another subset of the database dataset built for evidence detection. Here, each claim and opinion from the vector is context sentence and each component from the web is a target sentence. It also returns a dictionary containing all the claims with their corresponding evidences of any of the 3 types of evidences which we provided. The 3 types are study, expert, and anecdotal. The study evidences consist of quantitative analysis of data given as numbers or as conclusions. For expert, testimony by a person, group, committee, organization with some known expertise in or authority on the topic. And anecdotal can be a description of specific events, instances, or concrete examples.
Now for the evidence classification part, The dictionary from the previous model is passed to final CNN concat model. This model is trained on Stanford Natural Language Inference dataset, which is called SNLI dataset. It predicts if each evidence is entailing, contradicting, or neutrally supporting the corresponding opinion or claim. The probability assigned by the softmax classifier is the contributing weight assigned to each evidence. As example, for an evidence that is supporting an opinion, the higher the probability score, the more weight it has in validating the opinion. For each opinion, all the evidences will be ranked in 3 categories based on probability score. For each opinion, the top k evidences will be taken as supporting, contradicting, or neutral evidence. Finally, each opinion is stored in a dictionary with its corresponding detected evidences as keys. Opinions having no supporting evidences are discarded from the dictionary. Visualization of final output. Final output of the model is a list of opinions along with the relative percentage of supporting and contradicting evidences out of 100. For an example, take an opinion. Now, calculate the percentage of supporting evidences by taking the total number of supporting evidences divided by the total number of supporting and contradicting evidences into 100. Percentage of contradicting evidences can be calculated by taking the total number of contradicting evidences divided by total number of supporting and contradicting evidences multiplied by 100. Another way is to calculate the total weight of each of the supporting and the contradictory evidences to determine which side of evidences has the larger total weight. The weight is provided to user as credibility score. Visualization of decision-making process. Visualization of k most active neurons at the max pooling layer. For each sentence, whether context or target, we examine k most active neurons at the max pooling layer and highlight the words in bold who win at these k neurons in the max operation. For an example, Microsoft Office Excel could allow remote code execution. Here, Office Excel and code execution are highlighted in the bold. TSNE visualization, which is T-distributed stochastic neighbor estimation. Visualization graph plot these bold words in the word embedding space. Words with similar semantics should be close together in the space. TSNE visualization for opinion and claim detection. It should plot the tokens of both the topic and opinions in the word embedding space. Claim sentences should be close together to claim lexicons in the word vector. Opinion sentences should be close together to opinion and sentiment lexicons in the word vector. Visualization of decision-making process continue. TSNE visualization for evidence collection. Visualization graph should plot the tokens of each opinion and evidences in the word embedding space. Corresponding evidence sentence should be close enough to the particular opinion. Study, evidence, and anecdotal evidences should be close to their respective lexicon embeddings. TSNE visualization for evidence classification. Visualization graph should plot the tokens of each opinion and detected evidences in the word embedding space. For an opinion, their supporting, contradicting, and neutral evidences should be present in cluster. For an example, close together. There can be overlapping clusters of evidences as one evidence can be categorized as supporting to one opinion, however, can be contradicting to another opinion. These graphs for each subtask explain why a certain opinion is detected as an opinion to a particular topic, why an evidence is considered as contradictory to a topic, etc.
Now let's talk about the feasibility of our model. CNN is very fast compared to recurrent neural network. Our studies prove that concat CNN model outperformed LSTM-based RNN models in most of the argument mining tasks. Our model handles imbalanced multi-class data well during training. Our model provides end-to-end learning, simplicity in training and designing the model. Each of the components are trained on massive real-world data, which represents the scalability in the massive web corpora. Use of pre-trained word embeddings perform well on short as well as long text. Once the model is trained, it generates output in real time. The model can be deployed to create an opinion gathering search engine. Cost analysis. No hand engineered featured generation is required that is cost efficient. All the training datasets are available for free. Implementation will be done using TensorFlow. which is an open source library. For training, cloud GPU server will be used, which is free of cost, such as Floyd Hub, Azure, and Google Cloud. The only cost we have to bear is the server hosting cost. Datasets. We'll be using word embedding datasets that has more than 100 billion words created by word-to-vector tool. We'll be using ImageNet that has 14 million images from 1,000 classes of 20,000 categories. The third is database dataset. The fourth is Stanford Natural Language Inference Corpus, a collection of 570,000 human-written English sentence pair manually labeled for balanced classification with the labels of entailment, contradiction, and neutral. And finally, the click-through logged dataset by Microsoft. Now let's compare our model to the project Debater by IBM. We have provided an integrated end-to-end model which is capable of presenting all the claims and opinions to a topic with their corresponding evidences as opposed to their task-specific separate models. Our model is extended to categorize the evidences to their corresponding opinion clusters and assign individual contributing weights to them. Our model performs evidence mining on multimedia data along with text. Our model uses deep convolutional neural network, that is deep CNN, as opposed to their rule-based and feature-based algorithms.
I'm going to present our product prototype in the demo. So our application is SPDYBOT and this is the welcome screen. Now, in the search bar, you write whatever query you want to write. For an example, FIFA World Cup 2018. After writing this query, you click on the search button and all the results will be fetched with the visualization in terms of graphical manner. Now you can access any of the fetched item to have a descriptive look. As you can see, all the content with the positive, negative or the neutral percentage is given and it is visualized individually. Now you can go through all the different items and you can search them individually and have a look at it.
Now let's talk about the applications of our model. This model will serve the solution to the problems existing in the fields of e-commerce, politics, policymaking, government elections, etc. to resolve any controversial issue by reaching consensus. This model mines evidences for opinions so that the user can decide the authenticity of each opinion before taking them into account. Use topic-based opinions and corresponding evidences to create a knowledge base and build an argumentation search engine. Challenges. Our model cannot detect sarcastic or abstract opinions. Fake videos and images cannot be differentiated. Cannot detect if opinions are gathered by bots. Our model has to perform evidence detection on a large number of web pages, which can be costly and slower. Conclusion. We have provided a deep learning based end-to-end learning model using multiple cascading concatenated CNN models. This AI solution is capable of collecting all opinions and claims related to a topic and gather relevant evidences to determine if the opinions are supported by any evidences or not. Final output enables the user to either regard or disregard an opinion based on the collected evidences. We also included subtask-wise visualization process to understand how the model ends up with the final output from beginning till end. These are the references that we referred. So that's a photograph from the prize giving ceremony. We were awarded the third prize for our project by Mr. Alexander Bullris, who is a member of parliament in the House of Commons. In this competition, 52 teams from different universities all over Canada participated, from which top 8 finalists were invited to present in front of the judges in Montreal. Judges panel consisted of lead AI researchers, project managers, directors of Engineering Canada, etc. Thank you.